because k's and the z's and but those things are all known. What you're trying to find out is how does it scatter? What form does this f take? So that's what it's all about. So so if we take this two-part wave function, incoming and outgoing, and we subtract the incoming, then common sense says what's left is the outgoing or the scattered. And we want to work on this because we're trying to find what f of naught is. It's the whole point of the exercise. You're doing all this analysis on scattering, right? Okay, so the total. Okay, total. That's this and this or this. I mean, you're rewriting this as this, okay? But a sum of weighted terms. So that total wave function, this or this, is this minus the incoming. The incoming is this, so you subtract that. Now, the result that you get, in other words, this, the result that you get should not have any terms of this form. Why is that? Well, because terms of that form correspond to incoming wavefront wave functions, right? You don't want that. You want something of this form, that correspond to spherical outgoing scattered wave function. Okay, so you don't want anything of this form. So so the terms that are of that form, you want their coefficients to be 0, right? And again, this is a bit thrown at you. That means the scattered waveform here, which is all this minus this, which corresponds to that. That difference within it, if you have anything within that difference, if you have anything that's of this form that looks like an incoming plane wave, its coefficients, these, they need to be 0, so that you don't have any partial waves, if you like. You're adding waveforms, right? That's what the sigma here is. So those that look like a plane wave coming in, you want their coefficients, these a's here, to be 0, so that the only waves in your sum are of the form outgoing spherical waves. Right? I hope that you follow the logic. Okay. Now, again, this is sort of thrown at you a bit, but give you a feel for what's going on. So the fact that those coefficients must be 0, that allows you, that places restrictions, constraints on the value of these constants, and allowing you to actually solve them. Now, it's not done in the textbook. It's, like I say, this is just a sort of introduction. I give you a feel for some of the theory, but it allowed that removal of the waveforms that look like incoming waveforms from in your difference term, allows you to solve for them, and you get something of this form here. And these L's, where do they come from? From angular momentum, and this, these L's are quantum numbers. You can have quantum numbers for quantized energy, you can have quantum numbers for quantized angular momentum, and so on. They're integers, half integers, whatever, that label the value of the quantized physical thing you're talking about, like energy or angular momentum. So in the context of angular momentum, these L's here are just integers, okay? And they, like you might have angular momentum L0, or angular momentum with L as 1, or angular momentum with L as 2, and so forth. These quantum numbers. So this won't make any sense until you've thoroughly understood quantum mechanics of angular momentum. So you're going to have to wait until chapter 7, which is actually, I just recently calculated the number of pages per chapter, and the biggest is the next one on chapter 6 on the formal rules of quantum mechanics. That's 22 pages. This chapter 5, is fairly short. It's only 11 pages. So, and the one after that, chapter 7, angular momentum, is 20 pages. So it's one of the biggest in the book. So this is sort of thrown at you a bit. So you'll need to understand quantum mechanics of angular momentum, see where this L comes from. All right. Okay. So you now have values. That allows you to find numbers, the values for these coefficients A of L. Right? So that'll give you the scattered wave function. Remember the difference. This minus this term, which is all this. Throwing out all the values here that correspond to plane wave, incoming type wave functions that look like that. You don't want, physically you don't want that. You want partial waves, these alphas here, to be non-zero, only in the case when the wave they're talking about is spherical, outgoing, like a scattered wave, right? So the result that you get will be of this form, and so divide it by this amount, and that will give you your f of 0, which is what it's all about, right? You're talking about scattering. You want to know what your f is. Okay, so do all that, and you end up with something like this. Now I haven't put homework on it because it's too hard, right? You don't have enough knowledge. So this is in a sense just being thrown at you to just give you a taste of what scattering theory is all about. Scattering theory is mostly graduate level stuff, right? So here's what you get. Legendre polynomials, your scattering amplitude, your f of theta will depend on the delays, or the phase changes. And the phase change depends on the L, so you've got a delta sub L here, right? And so you end up with that expression. So in other words, written it here, the scattering is all about this f of theta. And this f of theta, if you look at it, is about these phase changes, these delta. Okay? So it boils down, the analysis of scattering boils down to calculating these deltas for each partial wave. Now we can start talking about what I mean by partial. Well, here you've got a sum of a lot of waves, right? So so if you just take like one of the waves, that's not the complete story, right? It's just one of them. It's like part of the story. So hence a partial wave. So for just one of these A's here, you'll have a corresponding waveform, and that's a partial wave. Okay. So now you know why this whole thing is called partial wave analysis. You're trying to find out, discussing what the phase change is, delta here. Hence partial wave analysis. All right. Now, before I run out of the session, run out of this quarter board, two squares. Note, have a look at this. Note that if all your phase changes, your deltas here, if they're all 0, watch what happens. Well, if delta 0, your sine is 0, so this term becomes 0. So each term that is sum is 0. Hence the sum itself is 0, and therefore f is 0. And if f is 0, there's no scattering. Right? If f is 0, there's just no scattering. So Well, that sort of seems common sense. So another remark you can make, which is a lead into the next session, if you know all your Ds, your deltas, if you know all the phase changes, then you know what your f of theta, you know what your scattering amplitude is. Continue on the next session.